Let's threaten it again. You're threatening, fail it early and often as well. Somehow you threaten it, it works. All right, so let's just do knapsack problem again because it's a good classic one. And so really, as we go through this, if there's anything that you don't get perfectly, just, you know, do something. You know, really, you're all alive. You know, you all can put up your hand, shout, scream, do something, right? Do something. All right, so the problem is that you know, we're a robber, and we have a knapsack of volume V, and the store has all these objects, and each object has a volume and a price, and our goal is to find a subset of the objects. So if S is the subset we're taking, then the sum of the volumes can't exceed the volume of the knapsack. Right? We're not worrying about fitting. You know, so maybe weight would be a better thing because then it sums better. Also, we want what we're trying to maximize is the cost of the price of the objects that we grab. Everybody get the problem? So, greedy criteria, if you grab them, you know, we did all these things here, right? These don't work. This one is kind of interesting, that it seems reasonable that what we want is the most profit for every little square inch, cubic inch in knapsack. We want the most profitable thing per cubic square inch, right? And so this is kind of saying, grab the object with the best cubic square inch, and then as long as the reason it doesn't give you the optimal is because we can't fill the whole knapsack. There's wasted space. But if we were doing a fractional solution, if you could put in a fraction of a bear, and the bear in the knapsack then was full, and you maximize cubic square inch, then life would be good. Right? People see that? But integers, as a general rule, integers give us a hard time and make things NP-complete, meaning that we don't have a polytime algorithm. And as we'll see in the end, as we showed over there on that board, that this algorithm is in fact exponential in the number of bits to write down V. Right? So this is in fact an NP-complete problem. If you could solve this problem in polytime, then you could do Satin polytime and you would be rich. Right? So, alright, so now we have an instance that we need to solve. We imagine that a bird has a solution. She knows what to put in the knapsack. We have to ask a question. Usually we ask a local question about the end of the solution, but we want it to have few answers as possible. So one way to minimize the number of answers she asks is we sort these in an arbitrary order, and we ask about the bear, and we say, do we put the bear in or not? And if she says, right, there's over here, we got to get up, do you take it or not? Right, so if she says yes, then you put the bear in, right? And then we ask our friend a question, and the friend's question is, we have all the objects except the bear because we understand the bear, and we've made his knapsack smaller, right? He gives us, what does he gives us? He gives the optimal answer for this smaller knapsack, and our solution is the same except we stick the bear back in that spare spot. Everybody got that? So if the easy case, if she says no, then we just get rid of the bear. The friend gives us a solution with the exact same solution minus instance minus the bear, and then our solution is the same. Right? Oh, I guess we kind of missed back here that when we put the bear in, the cost of our solution is the cost of our friend's solution plus the price of the bear. Are people following this? And you can kind of see how if you have a bird who tells you something local, and if you have a friend, then it's pretty easy, right? And all the difficulty in coming up with this algorithm is right there. All right, so again, if you were to run this algorithm, it would have exponential time. And so we want to find out what is the set of subinstances that ever arise. And given this instance, what are our friends' subinstances? And so, right, so first thing we'll see you know, this is a fine subinstance. You know, the bird can just keep saying no, and we would get this. Everybody kind of see that? If the bird says no, then we give that to the friend. His bird says no, we give that to a friend. Says no, we give that to a friend. Eventually we get to the subinstance. Right? So that was just graphically showing it. What about this guy? No, because we see it's always a prefix. We're always killing the objects in order. Right? And as a general rule, you like prefixes because they're poly-size. If you ask an arbitrary subset, right, then there's an exponential number of them, and that's a problem. All right, so and then so it's a prefix, but we can have we're going to allow any knapsack size, and this is what kills us in the poly time, right? Because we have so many knapsack size. Right, so maybe some knapsack sizes won't actually arise, but it's just as hard to figure out which ones will arise as to actually do it. So we'll just pretend that they're all arise. Right, so this is our complete set of subinstances. We have an arbitrary knapsack and an arbitrary prefix. Right, and how do we know that? What are the properties we need? We need that our instance is included. Right? Well, you have the full knapsacks and all the objects. Right? And then how is it closed under the friend operation? Right? If this person was invited to the wedding, right? Right? If this is invited to the wedding, who are this person's friends? Right? If you say no, then all you do is delete this last object, and that person's invited to the wedding. Right? And if you say yes, then again the last object, and this is made a little smaller, making sure that this is positive, so this person's invited to the wedding, right? So everybody's who's invited to the wedding's friends are also invited to the wedding. Everybody see why that's important? Right? Because the only way you solve a problem, everybody who's invited to the wedding needs to be solved. And how do you solve them? You get help from their friends, so their friends better be there too. Right? So here's the table. I guess I didn't have it switched from last time, maybe not. Anyway. What's this a particular subinstance here? It says we're considering the first I objects, right? We have a knapsack of size V prime. We want to know which of these objects to put in this knapsack to maximize a profit, right? So if she says no, then this is our friend, right? We eliminate the last object, and our cost is the same, right? And if she says yes, then we eliminate the last object and we make the knapsack smaller by the size of the bear. Right? And then we take the answer from our friend, but we add on the price of the bear. Right? Does that make sense? So we take the best, now we have the best answer consistent with taking the bear and the best answer consistent with not taking the bear. And of those two best answers, we take the best of the best. Right? Everybody getting this? What order do we fill the table in? In an order so that nobody waits. That means when you're doing this, his friends have already been solved. Right? Here's the code. It's so like any code. You know, you have your instance, and you have a table here. So what I don't like in this is it doesn't say what this instance is, right? It should say here v prime I is the instance. What objects are the first I objects you put it in knapsack size v, and the base case is when either your knapsack is empty or you have no objects. Maybe we just did the one case, and then here we're looping over all subinstances. Right, all values of I, all values of v prime, and now we're filling in this particular instance. We should know what that instance is. And how do you do it? Well, now we loop over all bird answers. Right, you'll note that there's no loop here. Why? Because there's only two bird answers. If she says 1 is when she says no, so you just eliminate the last object, right, and you take the same cost. And if she says yes, then assuming that the object fits in your knapsack, you put decrease the size of the knapsack but the size of the bear and take the bear out. And then the cost of your friend's solution, you add on the price of the bear, right? To give you the price of my solution, right? Everybody kind of get this, right? You'll know I tell a lot of stories about birds and friends and stuff because I think it gives you more intuition than writing this sentence down, right? It would be hard to just, what I see most people, a lot of people, they just teach you, put the code down and say, okay, here's the code, and okay, great. All right, and then down here, we take the best of these two, right? And we store the bird's advice, which is either we're storing 1 or 2, right? And the cost. Right, and then once you fill in the whole table and you have the bird's advice, then it's easy to redo it. Running time, right? Like all dynamic programming algorithms, it's the number of sub-instances times the number of bird answers. This is pretty innocent here, but we have to say, this looks innocent, right? It's the size of the knapsack times the number of objects. Right? And the question is that polynomial? But it's not, because this bit here is is exponential in the number of bits to write down v. Right? So if your knapsack was reasonably small, right? If you measured the size of your instance by the number of objects and kind of, you had to actually lay out the knapsack. Right, so the size of the input was the size of the knapsack as opposed to the number of bits to write down the size of the knapsack, then it would be polytime.
I don't understand why it's exponential.
Why it's what?
Why v is exponential.
All right, suppose I have 100. My input's going to be a size 200. All right, or about that. So I'll have 100 objects. Object 1 up to object 100. And that takes about 100 space, right? And now I'm going to write down v, and v is going to be a 100-digit number, right? So the whole thing here is about 100 size, right? And the size is about 100. But what's the time? Well, it's v times n, and what's n? Well, n's only 100. So, okay, so what? Right, the 100, it took him 100 times to ask me the question, so it takes me 100 times to solve the problem. No big deal. But what's v? V's 10 to the 100. Right? 10 being the base. This is a 100-digit number base 10. Right? If it was base 2, we could have done base 2, it would have been fine. Right? Does that make sense? I can write down this number, and then you have to do that, the value time, right? Right? If you had to, so what I was saying there is, instead of writing down this in bits, if you actually had to draw the knapsack on the board, then the size of the knapsack wouldn't be a big deal, because the size would be, right? If I had to put the knapsack here, and the knapsack was of size about 100, then this would just be 100. And then the algorithm would be quadratic, right? Because the input size would be about 100, and the running time would be about 100 squared. Does that make sense?
Kind of. I mean, I see if you draw it, it's quadratic. Why is it exponential otherwise?
Well, do you get this question? I have an input n, and actually let's call it input v. So this is our problem. Some problem p has an input v, and what the code does is loop I equals 1 to v. Right? Is this a polytime algorithm or an exponential time algorithm?
V is the input.
V is the input. All right, well, let's do it then. I will write down a number and I want you to count to it. Who's going to win this game? Right? Right? So, yes, the running time of this algorithm is V. But V can be a big number. Right? And people say, oh, this is silly. But it's not silly because it's the basis of cryptography. Right? I send the bank a 100-digit PIN, and that's by security. Right? Because the only way it knows how to, the robber can only break it by trying to factor it or trying to count up to that value. Right? And it only takes me 100 bits to write it down. So, that's why I get, big on this. And otherwise we get confused, right? We learn dynamic programming and we say, here's a great polytime algorithm for it. And then we move over to NP completeness and I say, hey, Knapsack's NP complete, and you're going to get confused, right? So, so dynamic programming takes this much time, which is polytime if the knapsack is small, exponential time if the size of the knapsack is an arbitrary integer, right? It's NP complete, which means that if there was a polytime algorithm for it, then there would be a polytime algorithm for all reasonable optimization problems, and as I said, you'd be rich, right? But there's likely not a polytime algorithm for this class, so there's likely not a polytime algorithm for the knapsack problem, right? Don't hope for it, right? I mean, you should, in general, you shouldn't buy lottery tickets, but this would be a worse lottery ticket, right? To wait for this one. All right, if you come to the grad class next term, we'll cover approximation algorithms, which means for every epsilon, you can make epsilon a teeny, teeny little number. Then there's an algorithm which can find an answer that is within 1 plus epsilon of optimal. And the running time is something like 1 over epsilon cubed or something like that. Right? So the smaller you make epsilon, the longer it takes you to run the algorithm. Right? And that's it. Everybody kind of get that? So I would definitely say by not next Monday, the Monday after, you better understand all of that. Right? So if you don't, now's a good time to start thinking about it. Everybody want to start a new one? Okay, job scheduling, right? The inputs we had before was a start time and a finishing time of these events, and we wanted to make sure you chose a subset that don't overlap in time, and we had the cost be the number of events that you schedule, right? So then we had a greedy algorithm, right? Remember what the greedy algorithm is? Is you chose the one who finishes latest.
I had a question about the semi-optimal thing, the epsilon stuff. Doesn't that imply that you actually would already have to know what all the potential optimal solutions are to know how close you are to getting one? Like,
life is magic. Come to the grad class. Yeah. I mean, how do you prove that my solution is within 1 plus epsilon of optimal? I mean, we prove it, right? All right, so everybody remember the greedy algorithm? We sort it based on the earliest finishing time is when you grab first, right? We grab this one, and that works great. All right, so now we're going to add weights. So every event also has how much the guy's willing to pay to schedule the event in your room, right? Oh, she did. Yeah, I guess they're still down there dancing. I don't know why. All right, so same problem as before. The cost, you schedule them so they don't overlap in time, and we take the cost to be the total weight scheduled, and we want to maximize that. All right, so if we took the earliest finishing time, right, that clearly doesn't do the trick, right? Note, in a counterexample, you need to say, what is the optimal? The optimal is the 100, while the greedy, gets 2. So you want to. And it was a little harder in the test question because it wasn't an issue of value, but you need an example where they could be stacked, but the algorithm wasn't stacking them. All right, so. And maybe we don't do it here, but the other obvious greedy algorithm is you take the object that's worth the most, right? And it could be really long, right? All right, so now we want to do this bird and friend thing again, right? We have an instance here. The bird has a solution. We ask the bird what?
Should I take...
We take the last object.
Or not?
Should we schedule it or not, right? Or it could be the first one, whatever, right? We take this last one, then we have too many answers, right? If we ask, what's the last object that we scheduled, then we would have to say all the possible last answers, right? Everybody got that? Right? But if we ask her, that last object, do we schedule it or not, then she answers yes or no, right? All right. If she answers no, what do we ask our friend? Right? We get rid of it. The bird says get rid of it, right? We ask the bird the same, and then our solution is the same as his. Right? Everybody get that? The same as we did last time. All right. If she says yes, then what do we ask our friend? We give the friend the rest. The friend gives us our solution, and then what is our solution? His plus ours. What's the problem with that? Ours overlaps with his, right? Exactly, right? Doesn't work. Why? Right, so say this was our last event here. The bird says keep it. Right, when we keep these, we can't keep any of these, right? So what we're going to give our friend is we're going to delete the one the bird says to take, and we delete everything else, right? Does that make sense? And then when the friend gives us his solution, this is kind of like the knapsack. We can put the bear back in, right? Does that make sense? You have to make room for the bear. Everybody kind of following this? All right, so that's great. And my cost is the same as his cost plus the weight. We have an exponential algorithm here, so we have to find out the number of subinstances, right? So let's just trace through this example, all right? Here's the input are those events, and you see how they're overlapping in time, right? And we want to see, kind of count how many subinstances will arise. So suppose we ask the bird about this last object, and the bird says, keep the 18. So if we keep the 18, we have to delete the 9, right? So this is what we give our friend. Everybody see that? Now our friend looks at the 17, and his bird says, reject the 17, so we delete the 17. Right? And then, so this is his friend, and his friend asks about the 16, and the 16, and the bird says, keep the 16, so we delete the 7. And this is his friend. People following this? Right? And then his friend asks about the 15. The bird says reject the 15, so this is his friend. And then this friend asks about the 14, who says keep it, so we reject the 5, and this is his friend. See the pattern here? Right? This guy says keep the 13, so we remove the 4. Now we want to know, and so we can keep doing that, and there's a whole tree of these things. Right? But each time they say keep it or not keep it. How many subinstances are happening here? A lot. Why? Because what left on this top row could be any subset, depending on whether, right, if they took the 18, then the 9's gone, and if they don't take the 18, the 9's not gone, right? So any subset can be here. Right? Every subset of those first 9 objects can arise as a subinstance. People kind of see that? And the problem is that a subinstance here is not a prefix. It's a subset. It's a subset of the objects. And as soon as you count the number of subsets, you have, right, how many subsets are there of n objects? Right, you got to choose, do we put the first object in or not? Do we put the second object in or not? Third object or not? That's 2 to the n choices, right? So there are 2 to the n subsets of n objects. Does that make sense? So the number of subsets here is way too big. The number of subinstances. So if we were to build a table, it would be of exponential time. Our running time would be exponential. Right? Everybody got that? So this is an example of a bad algorithm. In fact, for most problems, this is what happens. The reason we have NP-complete problems is because the number of subinstances grows exponentially. Right? I have to go to the wedding, and I have 2 friends, and they have 2 friends, and they have 2 friends, and they have 2 friends. Before you know it, you got a lot of people coming to this wedding. Right? All right. So now the greedy algorithm, we're going to just change one thing. Right? The greedy algorithm sorted the jobs by their finishing time. Right? And we're going to do the exact same thing. We're going to see this is the same set of instances. The only difference is I gave them different names. The order in which I complete them. Right? Now, if this is I ask about 18, and the bird says keep 18, then I delete 17. Right? Oops. Right, everybody see that? And now I ask about his friend asked about 16, and they said keep 16. So far everything is the same as it was. Right? But now look at what's cool now, is we don't ask about 14. We ask about 15. So now, if they say, whether or not, if he says keep 15 or not keep 15, either way, 15's gone. See? And so the cool thing is you go through this, in that way, each subinstance is going to be a prefix. Right? People buy that? So, they're only in prefixes, and so the running time is polynomial. So, this is what we're going to, if this is my instance, we have to guess a complete set of subinstances. And we're going to guess that the subinstances are all prefixes. Right? And so now, this is the, what does our set of subinstances need? Well, it needs to include our instance, which is clearly there, because it's, the full set is a prefix of itself. Right? Now, this is the hard part. This is the crux of the algorithm, is to prove that this is closed under the friend operation. Right? You have to prove that given any instance, right, any prefix, then all their friends have to be, needs to be a subinstance too, right? All right, I guess the question, wait, that one was easy. All right, so this is what we have to prove here, is that it's closed under subinstance. So we're going to do a proof by picture, right? Why do we do proof by picture? It's because we're lazy, right? And it's good enough. Otherwise, we would be drawing lots of math on the board and everybody would get scared. All right? So suppose that this was my subinstance, right? Which object do I ask the bird about? This one, right? The one with the latest finishing time. I ask the bird about that event, and if she says keep it, then what do we delete? We delete those guys, right? And the thing is, these are sorted by finishing time, right? So the ones that we delete are all the ones that finish after this point in time, right? And so you can see they're kind of a postfix. We're deleting a postfix. Right? Does that make sense? And so what we're keeping is a prefix. And hence, because it's a prefix, this prefix has been invited to the wedding and it's been solved, and our friend who gave us the optimal solution, it's in the table. We look it up in the table, right? And we add our instance back in. Right? Everybody happy with that? Right? So this is just kind of more proof by picture, right? Here's a typical deleted guy. It overlaps with the one we're keeping, right? And a typical undeleted guy doesn't overlap with who we're, right? And this one comes later than that one, just by the picture, right? So we're keeping a set of, right? Because it's a prefix, it's a subinstance, and life is good, right? So our table is now of size n. What is this instance here? This instance is sort the objects by their finishing time, considering the first 4 objects. Which of those should you keep to maximize your profit so they don't overlap with each other, right? These, in some ways it's more, it's, with more of the input, right? We pretend the input was the first 4 objects. What would our optimal solution be? Right? And now when we're trying to solve this one, we say, well, we either keep the last object or we don't. If we don't keep the last object, then the solution's here. Right? And if we do keep the last object, then we have to back off until we see which of these overlap. And it will be some prefix down here. Running time, number of subinstances times the number of bird answers. Well, how many bird answers do we have? 2. How many subinstances do we have? N. Is this the running time? Usually it is. That's all I'm going to ask you for. But it's a little harder because for the yes instances, you have to know how far to back off with how much is going to overlap. And so there's a little tricky there. And you can use, you can do binary search. Right? So at most it's going to take you an extra login time. Everybody kind of good with that? All right. How are we doing for time here?
10 minutes.
10 minutes. Any other questions? Because we're starting something scary here. All right. I warned you. All right, remember we did parsing, right? This was one of my favorite parsing algorithms. In fact, you were asking what's going to be taught in that 4th year course.
Yep.
I think I might do parsing. You might say, why? Well, I could give you one of 2 answers. One, it's one of my favorite algorithms, right? That's the true reason. But it's about, how can you prove that, Turing machines are equivalent to recursive programs, which are equivalent to Java program. Well, how do you get from Java to Turing? Well, you use a compiler. And how do you do a compiler? You do this. So it's kind of cool. Anyway, it's not really part of the course, but we might stick it in there. All right. And in this parsing, it was called look ahead 1. Right? Remember that the difference between this rule and this rule, the first place they differs in 1 character. And you can say, hey, yeah, what that character is, and you're good. And so this parsing time algorithm was linear. You just flew through the string that you're parsing, and it's way cool. Right? But now, right, remember get expression called get term, and get term called get factor, and so forth. Right? But now life is harder. Right? This is not look ahead 1 anymore. This is a grammar, right? Terminal T can go to an AB, and an AB goes to an AA or to a BT, right, or so forth. And Chomsky normal form. Mr. Chomsky was a linguist who came up with this stuff, right? We're going to have every terminal either goes to every non-terminal goes to 2 non-terminals, or it goes to a single letter. Chomsky normal form, right? It just makes our life a little easier, right? And right, that's what that says. And now we want to know, the problem is you're given some string and you want to build a parse tree for it, right? So here, for example, here's our string, right? Here's a parse tree, right? T goes to CA, and C goes to AC, and so forth, and you parse it. Everybody kind of buy that? Everybody understand what we're building here? And so this is still called, it's still context-free parsing, because what you're allowed to turn the C into doesn't depend on where the C's sitting, right? One thing that would be cool to do in that next course is talk about context-sensitive parsing, which is equivalent to Turing machines. And so, you know, can you parse this is the same as will this Turing machine halt, and that's hard, right? All right, so this we can do, right? Everybody got the question? All right, so what's the problem with the recursive algorithm is if you're Mr. Get Term, you don't know whether to call get A or get C or get T, right? You don't know where to go. Everybody kind of follow the problem of the recursive algorithm? So instead, we're given this string, and this is the string we're trying to parse, and we know we start from T. We want to know where to go, right? We're going to ask a bird a question, right? You're standing at T, you want to get there. What's the obvious question to ask the bird?
What's the next option?
Should I go to A or not?
Yeah, which of these three rules should I use? Right? So the bird tells you the first rule. Right? Now what do?
Ask his friend.
Right? Another question we could say is, what do we want to get from our friend? Well, as said, one friend, he's going to give us the left parsing, and the other friend is going to give us the right parsing. Right? So that's what we want to get from our friend. But the hard part is, what do we ask our friend? What instance do we give our friend? What's an instance? Is the start symbol and the string. Right? So, certainly what we want from our friend is that. Right? But what instance do we give him? We would like to give him the C, because he's starting at C, and we want to give him what he's parsing. Right? Do we know what he's parsing?
No.
No, we don't know what he's parsing. Right? So the problem is we don't know where to split. Right? If we knew where to split, then our friend would give us this, our other friend would give us this. Right? So how do we figure out where to split? Who's going to tell us that? The bird would tell us. Ask the bird. All right, so we ask the bird two questions. It's okay to ask a compound question. The question will be, what rule do we use first? And the other question is, where do you split? Right? How many answers are there for the first rule? How many? In this case, it's 3. Right? No big deal. Right? Number of rules for T. How many places to split? Yeah, n minus 1, something like that. Right? Everybody get that? 5 minutes. Excellent. You know, we're going to actually finish this in 5 minutes. And then you'll all be scared. Right? Because then we'll be done the course. I think pretty well. All right, except for the MP stuff. And that's harder. All right. Now, how many answers? This is how we ask the compound question. How many answers does she give overall?
2.
Oh,
No.
1.
How many possible different answers?
3 times.
3 times.
This times this, right? Because every one of these combined with every one of these, right? The number of answers is that times that. Not a big deal. It's still polynomial time, right? She gives us that. Then we give this to our one friend who gives us the answer. And then we give this to the other friend who gives us the answer. And then our answer is the combined. Everybody got that? Pretty nice. And there's the code. It's, you know. Now the question is, how many sub-instances do you have? Right? What are our sub-instances? Well, suppose this is our instance, so it needs to be in there. Right? And then maybe this is what the bird says, so you need this as an instance. Right? And then the bird says something, so you need this as an instance. Right? And so forth. So what are all the instances? Is, well, you could be starting anywhere. Right? Any of the non-terminals. And what's the string? Any contiguous subsequence. Right? For every I in J, we're going to go from I to J. Does that kind of make sense? And how many of these are there? No? How do you name one? It starts at I, it ends at J. How many choices for I? How many choices for J? How many of these are there? In squared. Why? Because it's not an arbitrary subset where you have to make a decision about each one. Right? Once I decide that this is there and this is there, everybody else is there. Right? Does that make sense? There's only n squared of those. Alright, how many non-terminals? Not too many non-terminals. We're good. Right? Number of subinstances is the number of non-terminals times n squared. Right? Here it is. Right? Our table. You wanted an easy guy. What's the table indexed by? IJ tells you, every square in this has to be a subinstance. Right? So what is a subinstance? I guess the panel here will tell you the start symbol. Right? I want to parse from starting with C. And then IJ would tell you I'm parsing from I to J. And then you think about who your friends are, you can play with it, and it's not so hard. Everybody gonna get that? Running time. Number of subinstances times the number of bird instances. How many subinstances are there? Number of non-terminals times n squared. Right? How many bird answers are there? The number of rules per non-terminal times n. So assuming your grammar is finite, is constant, if your grammar is constant, then this is n squared in the length of the string. Right? But that's not nearly as good as what we did before, which was linear time. Right? I mean, if you had to imagine some of the code that people need to compile, right? You don't want your compiler taking n cubed time. You just don't. Right? You know what I'm saying? And we got more to do, but we can do that next class. Alright, so we have at least 15 minutes left of this, and then we're going to do NP completeness, and then I'm going to keep giving you hard material until you ask questions. Alright? So every class, come with questions.